Thanks guys for coming out. Welcome to GOTO Chicago night. We're really happy to have Todd Montgomery here as a speaker. He is one of our keynotes this year for GOTO Chicago, and this is a great opportunity for you to see the quality of sessions that we will have at the conference. This year we have keynotes Chad Fowler, Anita Sengupta, Martin Thompson, Kyle Kingsbury, and Todd Montgomery. This year we have a new venue. It will be hosted at the Weston River North, which is close by and pretty central for everyone. And the dates are May 11th through the 14th. If you know anyone who is interested in doing crew, you can contact me directly. We're looking for new developers to come and lend a helping hand. And I guess that's pretty much it for me, so I'm gonna pass it off to Todd, and I hope you guys enjoy your night.
Thank you. So you'll notice that Martin and I are talking. You'll see Martin's picture a little later as well, because he's been involved in this work as well, a very key part of that. We're actually, in our keynote, going to rant a lot about several things. Software development, financial, tech, a lot of different things. So I think you probably enjoy it. If we don't offend you, please let us know, because that actually is our job in that keynote. So what we're going to talk about is an open source project that Martin and I have been involved in, about what it is, why we've done things, how things have evolved, and sort of what we're planning on doing next along with it. But before we get into it, I want to say thank you. There's a person sitting up here who has basically funded this effort, and he works for the Chicago Mercantile Exchange, Barry Dowster. So let's all thank Barry. So what is Aeron? Well, Aeron is a messaging system. How many of you use messaging systems? Okay, good. So that takes care of about half my presentation. Brief outline of what we're going to cover. If you've seen Martin talk about this, we're going to cover very similar things because there's a lot of things that are very relevant. But we're going to take a little bit deeper dive and sort of talk about how things have evolved, how the evolution of things have come about. So it's kind of a sausage making kind of talk. We're going to talk about how the sausage was actually made instead of just the end result. So the first thing is, messaging systems have been around for a long time. Why would you actually think about building another one? In fact, myself, I've been involved in building quite a few of them. So why would I want to put myself in the trial and turmoil of building another one? Well, if you look around what's there now, we have a lot of things which are feature bloated. There's a lot of features, there's a lot of complexity that's been added for very little benefit, in my mind. So the key part of making these things efficient and letting them run well is kind of been lost. So kind of wanted to look at that in a little bit different light. With that, they're not fast enough. If you look at finance specifically, latency and throughput, these things are just not cutting it. They're out there, they work, but they don't work well, right? They work kind of okay in many cases, but in some cases they kind of fall down. And another thing is, it's not just about having a low latency system, it's about having a low latency and predictable system. And this is what happens when it's not as predictable and not as low latency. You get hit in the face and it hurts a lot. And we really live in a different world. These systems, even the most recent systems, are still 5 and 6 years old. Technology moves a little quicker than that. So we live in a world where it's multi-core, it's multi-socket, it's cloud. But it's not just that. It's also that we have many different types of media that we have to go across. It's it's not just IP, it's IPC, it's InfiniBand, it's RDMA, it's PCIe. There's lots of different options out there. So we fundamentally kind of went in with the idea of trying a new approach with here. Getting rid of all the kind of preconceptions that we had about how things had to work and how they had to function. Which was, I gotta be honest, was not easy for me since I've written a lot of these before. But I was really very willing to look at these things in a very different light. And so the team is actually 3 people: Martin, Richard, and myself. And we kind of brought Richard in with the thought of we wanted to use a lot of different Java 8 features, and we wanted someone who was very familiar with Java 8 to give us kind of an idea about how things could be functioning there. We also had a different sort of goal in mind. We also thought that if we could get someone who was a JDK committer, we could actually show him some of the pain that we suffer, by being Java users, and hopefully get some of that change. So we'll talk a little bit about that much later. So when you start looking at this, you start basically building things from first principles, what features are really needed, right? If you just cut out all the crap and you start thinking things fresh, what do you need? Well, when you're thinking about messaging, you have subscribers and you have publishers, and you need to connect them, to one another. And you have to have a couple different things which are abstractions that you kind of hang your hat on. The first thing was we decided we wanted a channel, the idea of a communication channel, and within it, then multiplexing across different streams. So that gave us, the idea of how we wanted to connect subscribers, to publishers as well. We also noticed that we didn't want a framework, right? In the JavaScript space, we have so many frameworks and so many things which are very, they're not really providing much value. So we didn't want the idea of a framework that you had to work your application into. We wanted something which was much easier to sort of work in to an existing framework or an existing application. So we looked at it as more of a library than a framework, which kind of meant we wanted something that was much more composable. So we bared it down to bare minimums. We looked at things like, we wanted it to be equivalent to an OSI layer 4 transport for message-oriented streams. So if you break that down, what that means is you have a set of 5 things that you have to actually have. The first is a connection-oriented communication, which just means is that you have the concept of connection from a publisher to a subscriber. You have reliability, okay, and this means best effort reliability, not where a receiver goes down and you come back up and you get everything that was sent. And we wanted flow control as well. Okay, we wanted to be able to slow the sender down if the receiver was too slow. But we wanted it to be wide enough that there was large variance in that, a lot of ability to sort of handle bursts and things like that. Congestion avoidance and control is another aspect of this. That when different things are competing on a network, how do you handle that congestion and multiplexing? And so if we dive a little bit deeper, connection-oriented communication basically means there's a connection and there's some ordering associated with that, right, between a sender and a subscriber. Reliability means is that, you're trying to recover as best you can, but if you can't, or there's extenuating circumstances, you can still give up. Flow control meaning that you really want to try and slow down, but if things are too bad, you're willing to eject. And congestion avoidance and control meaning if there is congestion in the network, then you want to kind of back off. It turns out that in trading, you're willing to get rid of this. You're not really as willing to get rid of flow control, but you're willing to get rid of congestion avoidance in many cases because it unnecessarily slows you down, because it's more conservative. And multiplexing being the ability to have a communication channel with a handful of different streams within it. We sort of live in a world, which is multi-everything. We have multiple cores, we have multiple services. We have sort of a world where we have to be able to scale, and that really means that there's a large number of publishers, large number of subscribers, and they have very different aspects to them. So as we sort of started this process, we actually asked ourselves a couple things. How do we design this? And we had sort of a basic idea, which was very different from how a lot of these things have been done before. But we decided that we needed to have a set of guiding principles. So we came up with a set, and that's not the set. Okay, our set of guiding principles was different than this. Okay, there was a few that we didn't have. I'll point them out. So the first thing is, we needed to be garbage-free and steady-state running. Okay, we were going to use Java as our platform to sort of try out new things. We could iterate much faster with this. And so, but to be able to do this and really have something, we had to think that this was going to be garbage-free. All the way from a sender to a subscriber, had to be garbage-free. There was no other choice. We wanted to take advantage of the idea of smart batching. In other words, you shouldn't have to trade off latency for batching, okay, and throughput. You should be able to, it should be smart enough to realize how to do that. This next one, the third one, was not in our original set because we didn't think we could do it, so we kind of did not do it. We kind of had Lockfree as our concept. Non-blocking I/O in the message path, no exceptional cases. These are things that we knew would cost if they were in there, and they would cause outliers, and they would hurt latency. And applying the single writer principle. In other words, that means that if there's one resource, there's one writer to it. There can be many readers, but only one writer. And we didn't want to have a lot of shared state that had to be updated. Okay, so we wanted something which was very simple from the sharing of state perspective, and we wanted to avoid unnecessary copies. A lot of these things are, the same things that you see over and over again in trading apps. You see anyone who's doing Java and is very concerned about latency, they look at a lot of these different features. As we were doing this, the wait-free algos and the wait-free algorithms came into play as something we could do. But that wasn't until September. Up until September, we didn't know that we could do it. And then it was Martin and I working at, in Denmark at a conference where we looked at it and said, we can make this wait-free all the way through. And I'll talk about how we did that. But it took us a long time to actually get to that point where we knew we could do it. So it wasn't a principle we started with. It really comes down to three things. And this doesn't matter if you're what kind of software you're creating. First is architecture. Second is the data structures that are used within it. And the third is protocols of interaction. Seeing this over and over again with microservices and other things like that, where these three things matter tremendously. So let's talk first about the architecture of what Aeron does. Aeron's pretty simple. You have a publisher, you have a subscriber. Publisher is sending to a subscriber. It is simplex. There is no bidirectionality in that arrangement. If you want that, you do it on a separate connection. So, right now, that means that we can just have publishers sending to a subscriber in one direction and a separate connection going the opposite direction, if we need that. So it kind of makes things a little simpler. And that would be great if that's all you had to do, and you could put some cues on the front of the publisher to sort of control bursting and everything else. But the world's a little bit more complex than that. So we had to break things a little bit. We knew that we wanted different types of media to go, just shared memory, as well as PCIe 3, as well as the IP networks, and InfiniBand. So we had to break it. We had to have something which was setting between the publisher and the subscriber that could handle that different media, so that the publisher itself didn't have to know how to traverse that. We came up with the idea of, publishers, senders, receivers, and subscribers. Martin and I are very big fans of actually having terminology that matches what we think, so that, and naming is one thing that we obsess over, naming that we really obsess over. So we'll argue about certain terms, and this is one of them. So these terms to us have specific definitions, and they reflect in the code. If you look at the code on GitHub, you'll see sender, receiver, publication, subscription. These are those terms that we use, and they have very precise meanings. But what this means is that there is an IPC, we call it a log buffer, we'll go into that, setting between the publisher and the sender, and between a sender and a subscriber. They have very specific roles, what they do. But that's not good enough, because you can set this thing up, but you need some way of actually coordinating all of this. We have something called a conductor that handles the creation and all the administration of this. So once you have everything set up, things can go very fast, but you have to have something which sets them up. So in our mind, that's a conductor. But that's not good enough. We had to sort of put things in place where we had the concept of a client and a media driver. And so the media driver is responsible for all the protocol interaction, and it's on both sides, on the sender and receiver. And then the client interacts with the media driver with a set of different things. This right here encapsulates all the different communication that is done in this system. It's really a microservices architecture with very defined roles. And it's done between the different components. So the media driver itself is separated from the actual applications. There's a couple different reasons for that. You may be thinking, if you have known me in a previous life, is the media driver a broker, right? Is it its own application, its own daemon that sits there? And much like Facebook and relationship status, it's kind of complicated. And it's complicated for a couple different reasons, but it's complicated in the fact that it can be run standalone. It could also be embedded. But essentially, at its heart, what it's doing is a core-to-core, being a CPU core, handoff of memory. Okay, so it's handing off data, memory that's on one cache, memory that's on another cache. It doesn't matter that it's in a processor. This is very different than a standard broker, which is usually going through the operating system and get to each side. In this case, we're not even going through the operating system. We're actually going through just the memory subsystem. And it's also about the isolation of the protocol logic. Once you isolate the protocol logic away from the application can do whatever it needs to do. And that means that if it needs to pause for some reason or do anything that might block, it's not going to affect the protocol processing. So it's a little bit complicated in terms of how the relationship of this is. But coming back to it, so that's the architecture. The data structures, we actually have a set of them. We have some maps, some primitive maps, and some other things we use internally that don't generate garbage in the Java world. And we also have some ring buffers and what we call a broadcast buffer, which is something which can drop messages. And we have some inter-thread communication, that's the IGC queues. And they're pretty fast, they're pretty nice. We also have a dynamic set of arrays, which are kind of useful, have certain properties that we needed. But the last thing is the thing that has really just very much influenced the protocol design as well as the data structures. And that's something we call a log buffer. So what is a log buffer? Well, it goes to the heart of what Aeron is. What Aeron is trying to do is not trying to send messages and send a string of messages. It's actually doing something much more all-encompassing. It's trying to replicate a log of messages from one place to a set of places. That's a very different approach. So this is what we thought of at the beginning. We wanted to be able to do something like this, just replicate it. So the question is, how would you actually do this? Well, let's think about this for a second. If we were to take a file, let's say we think about it like we would think about a queue. You've got a pointer to a tail, and you're going to add a message. So you go and you increment the tail, you put the message in there, maybe the message has some sort of header attached to it. And if you want to do something like just send that out on the network, you can send all of that, right? And just send it out on the network. The other side can then you receive it, and now you've got it replicated. You can send another message. Looks just like this. Let's break this down, because those log buffers are actually lock-free and wave-free structures. And this is where things get a little bit more complex. Let's break it down to the components of the steps that you would have to go through. The first thing is you increment the tail. What this does is sort of, if you've ever been to a deli and you get a ticket, and then someone later on says, hey, here, number 10, what's your order? That's kind of the concept. You increment, you grab that slot, that whole region. Now you can do with it what you want at your own pace. So the first thing is you write the message into it. And now the message is there, but you now have to basically tell the other part of the system that it's ready to be consumed by them. We actually, at that point, write the header. And once that header's been written, that's then an ordered memory access that then can be seen by someone else. It's now visible. So until that header is written, that message is not there. Just the tail's been written. That's a very key part we'll get to in a second. What this means is that it's a persistent data structure in the functional sense, not in the persistent to non-volatile memory. Which means that it's safe to read without locks. You can actually read that structure. As long as you read the header first and make sure it's there, then you can read that. And you can read that without a lock. So it's lock-free. We'll get to why it's wave-free here in a second as well. So a couple questions, right? We look at this and we go, okay, So it's a log of messages that are written like this. It's the same thing that's sent on the network. Okay? Oh, all right, that seems pretty easy. But does that mean that you have one big file that goes on forever? Well, no, you can't really do that. If you're thinking about this as a real system, you can't think about all the different things that would have a really large file, right? The OS would have to handle in its virtual memory subsystem. So, this is just a few of the things you have to think about. Okay, so we can't have one big file. Lots of small ones? Well, it turns out you have the same problems. Well, what if you were to reuse these things? Okay? We came up with something that was, pretty simple. The idea of, having an active one, a dirty one, and a clean one. In other words, wash one, wear one, right? So if you've ever traveled a lot, you eventually get to the point where it's like, okay, how few pieces of clothing can I put in my suitcase, right? Can I get away with just, a couple shirts? Can I get away with just a pair of pants, right? It's kind of the same thing here. How few of these can we get away with? It turns out that 3, yeah, you can figure out how to work this. 2 is harder because there's a lot of edge conditions you have to worry about. It's kind of like, you're going for 7 days, take 2 pairs of underwear or take 3. 3 may be a little easier. So the idea is, that there's one active, there's one that's been filled, and then there's one that's been cleaned. It's ready for use. How do we stay weight-free? Okay, so lock-free is there's no locks, and lock-free has the condition, from a very specific standpoint, that at least one thread can make progress. In other words, you can have one thread that will make progress. That's the key to being weight-free or lock-free. What does weight-free mean? Weight-free means that you're lock-free. You can always make progress, but it means that every other thread that is involved in that operation will complete in a certain number of operations. That's a very hard thing to do. So at GOTO Chicago, the presentation that Martin will do is how to design weight-free algorithms. Okay? Working with him for a couple of years now, I've seen how some of these things work, and we'll go into how this works here. But there's some subtleties. There's a lot of subtleties around these things. But his presentation is going to be fantastic. So if you're not planning to go and you're interested in this, please think about it. So how does this structure handle it? So the first thing is, let's look at it as if we had 2 different threads trying to add a message at the same time. Okay? So they each have to complete, and they may not have to complete successfully, but they have to complete in a certain number of operations. In other words, they can't sit there and wait for something, right? So the first thing that happens is that the first one increments the tape. This is an atomic operation. On an x86 architecture, it would be the equivalent of a lock-x add, which is an atomic operation supported by the CPU. Most CPUs have this as well. It means that if there's 2 different threads or even processors trying to do that same piece of data, it's a shared atomic operation. It will complete a certain number of cycles. So the first one tries to add. Before anything else can be done, the second one increments. And there's a reason why it incremented past the end. I'll show you why. At that point, either one of them can fill in what they want to do. Let's just say that the first one fills in its message and its header. At that point, it filled it in quite fine. It's basically grabbed its ticket from the deli counter. It's then done its work. And now it's done. Fixed set of operations. The second one, he could have been, very simple, and he could have written it just within memory, and it still would have been quite fine. But that's kind of a boring example. We're going to use one where it actually incremented past the end and see how that's handled. At this point, he does not complete successfully because he can't put all his stuff in there. So what we do, we pad that out. In other words, unused space. We then roll to the next one. He then tries again. These are 2 different operations. The first one, putting the padding in, completed within a very short period of time. He then goes back and tries again, which then he's successful. That's why this is weight-free. We don't have to wait to put that in. So what does this seem like from the athlete, someone who's setting out from outside? They've written the first piece of data. They tried to write one. It has failed. They then try again. Could they be trying this in a loop? Yes, they could. And they would fail if they were doing this over and over again and kept getting that edge. But that's not the wait-free part. The wait-free part is each of those operations will complete, not the whole thing. So it's a very, very important distinction. That's how it's wait-free, why those operations are, the way they are and how they operate. So, that's the basics of filling in one of these. We've talked about headers, but what's actually in a header? And I call this protocol porn. It's basically your old ASCII art. RFCs from the ITF, use this. Us protocol guys, we can't get away from this at some point, just laying things out so that we break them down. This did not look like it does today when we started. This is actually very simple. You have a version field, you have two little bits, begin and end, so that you can support fragmentation. You have some flags, which are unused. You have a type field, which tells you if it's a piece of data or it's some other piece of protocol mechanism between the sender and receiver. You have a length, which is this header plus the data. You have a term offset, which is where in that that file it is, or the term. We call it a term. A session ID, stream ID. These are things that we use to identify a stream. And a session within, or a session at the higher level, and a term. In other words, which one of those rotations we have, and then we encode the message itself. What drove us to come up with this? Well, the first thing is we looked at all kinds of different ways that we could encode this. And we wanted something which was the same header on the wire. In other words, we could send just everything out, and what we had in memory. So we wanted the same thing, which meant that the data structure itself had to actually understand this header. Originally, the frame length was 16 bits. It was squashed. And we had the concept of, if you're familiar with IPv6, the sort of concept of chaining headers together before you have data. And we didn't send alignment and padding and everything else. And we also had a fragmentation header. Well, the things that happened were, as we started to think about the data structures themselves and how they had to read memory and memory access and everything else, 16 bits was too small for the frame length. 32 bits is what we needed for the architecture to work. 16 bits just meant that we were, if you've ever heard of word tearing, it was tearing it apart, and it was just slowing it down arbitrarily. We ditched that. We just made the frame length bigger. We got rid of the header chains because we didn't actually need all that complexity. It's great. It allows us to add headers and different things like that, but all it did was make it so that the header was a variable length structure. So we looked at it and thought, well, we could just simplify this. We don't need all that additional stuff. And if we need it later, we'll figure out how to add it. Because we just relentlessly tried to simplify it into what does it need to do and get rid of stuff it doesn't need to do. And just simplify. We also figured out that we actually don't suffer a problem by sending padding, right? We're trying to replicate that structure. If we're sending padding, it's fine. We don't have to send all the zeros, but we can send the information that tells us that there's padding there. So sending padding and even aligning, in other words, padding things out to another cache line or another padding boundary. Just send that alignment. It's only at max, like 8 bytes. This is not a big deal when you're going at 500 megabits per second. Right? It's not a big problem. So it's kind of just noise at that point. So we relentlessly just looked at it and said, okay, this is meant for high performance. It's not a bad thing to go ahead and send this. We're replicating this log. We also looked at fragmentation. If you've ever looked at protocols like PGM, or you looked at IPv6 or before, fragmentation, how fragmentation is done. No, IPv4, not IPv6. You'll notice that there's a lot of information that's in there, like the maximum length and the offset and other things. You actually don't need that. You're just replicating that log, and something that's reading it just needs to know where that you start a fragment, that you end a fragment, or are you in the middle. That's all it needs. So we got it down to 2 bits. And the last thing is, as we were developing this and we were playing around with it, we came up with this concept of what we call a position. And it was something that started out as a simplification for flow control, and it's now been something that has influenced the everything all the way from the sender to the receiver and monitoring and everything else. So what is a position? What does this mean? We inadvertently, by doing this replication, found out that we could uniquely identify a byte within each stream across time by a tuple. Stream ID, session ID, term offset tells you a byte. That's actually 32 bits, 64 bits, all the way up to 128 bits of information. That's enough, that you can identify each individual byte across the stream within time. So what a position is taking 2 of those pieces, the term ID and a term offset, and it's just doing math. It's taking the term ID, multiplying it by the size of the term, and adding the offset. In other words, which term are you in, plus the offset within that term, that tells you your position within the stream. It doesn't tell you which stream, it just tells you within the stream. And because we're not afraid to waste memory, we decided that if the term size was always a factor of 2, we could get rid of that actual multiply and just make it into a shift. So that second thing is the actual calculation we do. So what that means is, you can easily come up with the position. And by definition, if you know the position, you can also get the term ID and term offset, in other words, the reverse, just because it's math. Very simple. It took us a long time to realize this. We're working on it. We're basically working around the fact that we have different terms and different files and how to actually map it. And then we realized we could do all of it with math. So it took us a while to break it down to that. So that's kind of sending. And we saw about, adding things. It's just sending what's there in the log. It's a very different kind of protocol. If you look at it from the standpoint of something like PGM or SCTP or any other type of protocol I've worked on before, none of them do this. They're always sending data and then they're reconstructing for some reason. This does not need to. Whatever's sent on the network can be replicated, in memory, and it uses the exact same structure, the exact same header. I don't know of any other protocol that does this. Maybe they exist, but maybe I just don't know. But how do you replicate it, right? How do you actually take it from one site to another? Well, you can send the data. These are just pieces of data, but you have to have a protocol around it, to be able to do it. And it's a protocol, right? It has the same semantics that you would normally see in any other type of protocol. So I want to quickly run through what the protocol looks like. You have a sender and receiver. Data is sent. But before you can do that, you have to actually set up a connection. This is like your TCP's send, except setup actually has all the different pieces of data that you would need, like term size and the initial term ID, some other things in there. It's literally set everything up. Let the other side have all the data it needs so that it can just string. Now you can't just have a sender that goes, sends a setup and then he just slams data through, right? First that's rude. Protocols are about etiquette as much as they are about, the actual exchange of messages. And so you do this by saying first, setup, here's what I'm going to be doing. And the other side says, that's cool, we can do that, status is okay. So it sends a status message back. It basically says, you're good to go ahead and send. And there you just start sending data. And you send it as fast as flow control will allow. So as you're sending, there has to be some amount of data that's being sent back that tells you what the status is and how much you can send and letting you keep going and that speed that you're going. At some point you may stop. So there has to be some sort of heartbeat to do a couple things. The first thing, it has to tell you that the source is still alive. Second, it has to tell you where in the stream or the position that the sender is sent up to so that if you've lost the last message, you can know to request it. And by definition, if you have missed it, there has to be some way of requesting it. That's called a negative acknowledgement or an ACK, and then a retransmission of that piece of data. That's it. There is no other types of messages. We're done. Okay, not a whole lot. Some subtlety, yes, but not that much. It did not start this simple. We actually used to use zero-link data frames for setup and heartbeats. We thought this was simple. We thought we were very clever, and it totally fell on its face. Okay, so it fell on its face for a variety of reasons, primarily because the data structures were not set up to have a zero-link message followed by a non-zero-link message in the same position. So we had to adjust. We also had negative acknowledgements that had a range of things that they missed, like a scoreboard, right? I missed this range and this range and this range. Turns out you don't need that. You just knack a range. So a whole range of different things that are missed, or just one range. We originally didn't send padding or frame alignment. We decided to go ahead and send it because it was small, one, and besides, it actually caused us to do some kind of gymnastics. We actually had to contort ourselves in various ways to be able to do that, which was slowing us down. So we decided, that whole set of conditionals, we can just get rid of those. We go faster when we do that. And it all revolved around actually taking out the special cases. So as we looked at the protocol and as we had started with something which looked pretty primarily like an IPv6 and like normal protocols that you might see in the ITF, we quickly just started to get rid of certain things because they just weren't needed. If you're trying to do this simple thing of replicating this data and having the data structures also be the things that you're processing on, it required us to actually eliminate a lot of that. So, this is pretty much how we kind of thought about things. We just kept simplifying and getting rid of the special cases. And what we came about was, something which reassembling messages is really, really simple. Normally when you're having to, even in TCP, when you're having messages come in and they come in different places and you have to keep track of what is going on, the complexity of that can get a little overwhelming. If you look at some kernels, you'll see the gymnastics that even TCP goes through to track all this. We actually figured out a way that's a little bit simpler. If you're on the receiving side and you're receiving data, you have two things that you keep track of. First is the completed, in other words, I'm contiguous up to this point. The second is the high watermark. They work a little bit like this. This piece of data comes in, if it's complete is moved, and high watermark is moved. Well, what happens if a piece of data comes in, but it's not complete? In other words, there's a gap behind it, like that. Well, high watermark can move, but the completed can't. It can't move until it gets filled in. Just keeping these allows you to basically know when there's a gap, how big the gap is, and actually how to fill it. So this actually is a simplification. It actually turns out to be a very simple part. It simplified a lot of our processing to just think about these things like that, and we only have to keep track of an integer, or actually two integers in this point. So as you send through, you've got a subscriber who is reading these structures, and he can only move once he has everything completed. He can receive up to completed. But he may not be consuming everything up to completed all the time. He may be back somewhere. He may have just processed message 1 and getting ready to get message 2 when message 3 comes in and is added. So the question is, how would you do something if you know that you have to keep track of the consumption of that by a receiver separately? So we thought about this, and originally we had it as part of the data structure. So a receiver could kind of, keep track of a count of where it had consumed. But we realized that was kind of a very limited way for us to do it. So we actually broke it out. That's when we came up with the concept of position and broke it out so that it's not part of the data structure. When you think about it, it's not a property of the data structure, it's a property of the consumer itself, like a subscription. And we thought about this and we realized that it's actually more than that. those different components that I listed, publishers, senders, receivers, subscribers, they all keep position counters. In other words, where in that stream are they at any one time? So if you look at that whole thing, where you look at a publisher, a sender who's sending on the network, a receiver who is receiving it off the network and placing it into a log buffer, and a subscriber, they all have position information, where they are in that stream. This actually simplified a lot of stuff. It simplified flow control, it simplified the way that we actually implemented it. It totally changed the way that we thought about it. In fact, our latency dropped dramatically once we had adopted it. We have one small place where we don't do this yet, and that's being changed as we speak. And it's really these counters, because they're really counters, they're just a log, right? They're key to flow control and monitoring. You can read, you can just sit there and read the memory where they are, and you can tell where a publisher is, where a sender is, in other words, how much is made it out to the network, where a receiver is, in other words, where it has received up to, in other words, its high watermark, right? As well as where it is completed, and where a consumer has been. All these are their goal for monitoring, because it tells you exactly where every component in the system is, through the whole thing, where they are in that stream. Flow control. There actually is not just one flow control tool. Because there is flow control between a publisher and a sender, there is flow control between a sender and a receiver, and there is flow control between a receiver and a subscriber, and they use different mechanisms. Counter is used between the publisher and the sender, as well as between the receiver and the subscriber, but on the network there has to be status messages that are used. Status messages are just the completed position of the subscriber and the window. In other words, how much it's allowed to send. Okay, it works exactly like you would think of TCP. In other words, I've acknowledged up to this point. Past that, I'm willing to take this amount of data sent to me at any one time. Anything beyond that, I ignore. Okay? Anything before this, I ignore. I only look at that window. And as I acknowledge data, I can then send more. That sliding window principle, it's the same thing. It works very, very well for flow control. So status messages are sent back periodically, to basically move this window along. So what triggers the sending of these? It turns out that you only need three things. You only need to know when a term is rolled over. You only need to know as you progress through the term, and that quarter of a term is something that we just basically picked out of the air. It seems to work fairly well. Or if you stop sending, in other words, you send and you stop, at some point you need a timeout to tell you, because something may have gotten dropped, you need to have a timeout that sends a status message. Which means that flow control is actually clocked by sender data rate. No special handling is required, no additional kinds of things. It just sort of works. By the way, why was a quarter chosen? Because it's a power at 2 and it's easy to use. Okay, the math just works out. So that seems interesting, a single sender, a single receiver. What happens if you were to do multicast, right? Well, there is flow control strategies. And we've done a simple one, which is basically the one that moves the fastest is what clocks everything. But we've basically broken it out as a strategy that you can then do composition of statuses from multiple receivers. We've been looking at these off and on of different types of strategies. Right now, what's committed is the simplest MAC strategy, but we also have preferred. In other words, you can ignore certain people and only look at certain other ones. You can also look at the quorum, in other words, the point that the majority has reached, and another one which is basically the minimum. So once we get those stabilized, we'll put them in. But these are, our guesses about what could be useful. But there also has to be a safety part. If a receiver totally goes away, you shouldn't have a sender that just keeps blabbering on, right? If you guys all up and left, I may stand here and keep talking, or I may stop, okay? If I don't see people nodding their head or laughing, I'm probably going to stop at some point. It may not be till 3 a.m., but it would be at some point. So there has to be, the protocol has to work in such a way that if there's no feedback, things stop. Okay, they don't progress. So you'll notice if there's no status messages, there's no completed progression. In other words, it doesn't keep moving, and there's no signal. Right, so it stops at some point. You may have a little bit of buffer where you'll send a little bit more, but at some point you need to stop. Now we mentioned congestion control. Congestion control is, in most trading systems, one of those things you're willing to trade off. Okay, you really don't care. It's a controlled environment. You're really not that concerned about these competing flows and being fair to one another. And TCP's congestion control is extremely conservative. So it backs off really, really far when it notices that there's some loss. The reason why it does that is so that it can come to a nice equilibrium where everything is nice and shared. Okay? It's a sharing economy, right, with TCP. Trading is not about sharing, right? So you're willing to give that up. So this is one of the reasons why Aeron does not get you congestion control. But if you wanted to do congestion control, how would you do it? Welcome to my dissertation topic, which I've never done completed yet. Like most academics, I sort of put education on the back burner at some point. The piece of information there is status messages. The first is how far you've gotten. The next in the window, in other words, how much you're willing to accept. With TCP, it has the same concept. The congestion window in TCP is managed on the sender. He basically kind of guesses at what that capacity is. The receiver actually knows what that capacity is from his perspective, so he can actually manage it. So all that happens with congestion control here, that window is dynamically adjusted based on loss. If you want to be friendly to TCP, as long as you receive data, you increment it. When you have loss, you decrement it. In other words, you multiplicatively come down. That will make it so that you're fair to all other traffic. Very well understood part of TCP. It's just flipping it so that now it's all controlled by the receiver. So, again, that's not something we've done, but that actually should work. And would be interesting to play with at some point. But that's not in the sweet spot of the different use cases that we're looking at. The things that we have knew. We knew that loss, throughput, buffer size, they're all really strongly related. They're almost impossible to decouple, right? You have loss, your throughput's going to go down. How much? Well, if you're doing flow control and you're not doing congestion control, it's going to go down a certain amount. If you're doing congestion control, it's going to go down a lot more. Buffer sizes, how big terms are, and different things like that. They do have, an impact on everything. So it's that interplay between those different things. They do have, a bit to do with it. The tests we have run, we've been able to do some extremely high throughput. But to do that, we've had to make the buffers bigger, and we've had to make sure we don't have loss. And we've had to to tune things in a different way. The nice thing is, we haven't had to do that for latency, because latency is pretty much static. There's no additional tuning you have to do. It's only when you want to do the really high throughputs, like out of the box you get maybe 6 or 7 million messages a second, really small ones. If you want to go up to 20 and we've even gone up to 25 million, then you have to actually make the buffers bigger. The reason why we don't just make the buffers bigger offhand is because some systems don't react well when you really make them really high. So a tip, and I've been talking about this for years, know your networking parameters for the OS and how to tune it, what they do, right? If you're using TCP, there's a lot of things that you can do to actually increase TCP's behavior by tuning those parameters. It also has impact here. So I've kind of mentioned how things work and what we kind of started with and different anecdotes about different things. What else did we discover? And this is the ranting part of this. So we chose Java, right? Because Martin and Richard and I are very familiar with Java. We can do a lot of different things with Java very quickly. There's great tooling. We thought we could could try things out really quickly. It turned out we could, but there's a lot of parts of Java that really, really suck. So the first thing is, can anyone tell me what a signed byte is? One of these days I'm actually going to get someone to tell me this. I have no idea. I don't know what a signed byte means, right? The lack of unsigned types makes parsing a little bit harder and marshalling a little bit harder. But that's not the biggest sin that Java had. How many of you have used NIO really at high speeds? Do you like it? Probably not. It is really bad. The locks within it cause a lot of contention. They cause a lot of outliers. I have a whole talk that goes into part of this. One of the pieces is within datagram channel, there is 3 different locks: a reader lock, a writer lock, and you would think, oh, reading should be fine and writing should be fine. They shouldn't contend on one another. But there's something called a state lock, and that is taken by both the reader and the writer. So if you have something which reads and writes, it contends on the state lock. Awesome. Off-heap, pause, signals, different things like this, when you want to go really fast and very close to what the CPU can give you, you have to go into different parts of things. You don't have access to the x86 pause instruction, which would be really, really nice if you're doing something which is sitting there just polling, which Aeron does a good bit of that. Even accessing signals, kind of painful. String encoder. How many of you have done like grabbing a string from a byte buffer? You have to create a character array to do this. So you create a lot of garbage, which means that if you want strings, you're going to already create garbage with the string, but actually having an intermediate thing that has to get created is just, less than desirable. It was very funny to watch Richard as he actually needed to get a string, to not have it there, and then realize this is kind of stupid. So he filed a bug against the JDK about there should be this method. He even wrote the method and put it there. And they said, it's not needed. I can't say anything more. Managing external resources. Since, Aeron does a lot of things where it's talking about a byte buffer, a mapped byte buffer, where it's mapped things into files. There is an easy way to map, but you gotta let the garbage collector unmap. So we do some things where reflection, where we grab in there, and there's actually an M unmap function. We grab it out and we actually unmap underneath of that byte buffer. Which means that, if you've got a bug and you access it now, you close the whole JVM up. But, there's no way to actually manage that external resource. In Java, you can close a file. You can't close a memory mapped file. Okay, you can close the file, but you can't close the mapping. Selectors. Okay, selectors create a lot of garbage, no matter what you do. They're also not Java 8 friendly, so you can't actually do like nice stream operations on them. It's one of those things that when you look at it, it's just, in Java 8, it seems like it's missing. And it creates garbage no matter what you do. So we borrowed a thing from Netty where we went in, grabbed it, and then was able to, with reflection, exchange the selected key set and with our own that didn't generate garbage. So we borrowed a play from Netty's book to be able to do that. There's things that are bad and you had to work around. And to be honest, every language has this. I mean, I've been working with a lot of C and C++ for years. There's a lot of things that drive me absolutely crazy, and and they're just as bad as these things. There's lots of things in Java that are really, really nice. Tooling. Tooling is fantastic. You've got great IDEs, great interactions. Everything from Eclipse to IntelliJ. This is why we chose Java as the first thing we wanted to. We wanted to be able to change these things quickly and have the tooling that made it easy to do that. And it did. We tried Gradle. I've used Maven, I've used Ant. This was a chance for us to use Gradle. Martin has a real hatred for Maven, so we were not going to use it. I was fine with that. So we got, Gradle is actually a really good build system. It has a lot of different things that you can do. It's very powerful, and it's actually very easy to use, and less fascist than others. HDR histogram, Gil Tinney's work from Azul. We use HDR histogram because we need to have those percentiles for latency measurement. We need to understand, those things. Great tool. Now that's That's across languages now. HDR histograms in a bunch of different languages. JMC, for profiling. We use JMC very heavily to really understand what was actually going on, what was hot, what wasn't hot. Where should we look? What was showing up in the profiles. Very important for us. Bytecode instrumentation. Actually, we decided to not use a lot of this. There's none of it, but we actually have, it actually allows us to do some things that, we would like to do later on. More of that, in a few months probably. Unsafe, some additional things in unsafe. Primarily you have get and add and get and add increment, which are nice, which are just access to lockxadd, which is a core part of our data structures. Really, really good. The optimizer is probably one of the things that Java has that is underrated. It can do an awful lot of stuff that by hand is pretty painful. Class hierarchy analysis and some of the other things, if you know how to take advantage of it, which means that we actually have a love-hate relationship with the optimizer. When the optimizer does things well, we look at it and we say, that's my boy. When it won't optimize and inline stuff, we look at it and go, I absolutely abhor you. You suck. So it is literally a love-hate. There is not a middle ground in this. Which is pretty much how most optimizers, whether they be ahead of time or not, really do. And the last thing is garbage collection. Some of the data structures that we use, we actually defer that garbage collection. It makes our lives simpler from a design standpoint. So it actually is kind of handy. Certain structures really would work really, really well with garbage collection. So what is next? Right? What are we looking at? And so I know I've thrown a lot at you, a lot of it's been anecdotes, but I want to sort of give you an idea of where we stand. We've done several passes of profiling and tuning. We do this actually sometimes on a daily basis. We've done a lot of different things where we've looked at different profiles along the way and concentrated on certain places, and it's really pointed out, where we should change things. Where we stand is it's really, really easy, even on just this laptop, to get 20 million 40 byte messages per second. Throughput, we don't have a problem. And you don't have to tune it for throughput. You have to adjust the buffers, but those same settings will work fine when you just want to see what the latency is like. And, this is just making the buffers bigger. There's no perfect size. You can just keep increasing them, and at some point you kind of reach the max. And you can keep going. It just means that you're now using more memory than you're actually going to return on. Martin has done up to 25. I've done 24 on this laptop. So it can go very, very fast. And we're not stopping it, because we still have a lot of stuff we can do to make it things we think we can make it faster. The second part is really the latency distribution. Latency is not a single number, it's a distribution. So, this is sort of gives you a kind of a HDR histogram style. This is a few months old now. It actually is better now than this. Sort of the up to 90%, you're very, very flat. Once you go up into the, a couple nines, even up to 3 nines, you're not growing that much. And even when you start getting up into the higher ones, you're still not growing that hard. Any system that has locks in its path will start to jump. And probably in the 4 nines and 5 nines, it starts to really jump up to very high levels. And this is Java. We've had various reports of, how this compares to other messaging systems. Martin and I don't have access to any of them, so we haven't done it, but we do know of friends who have done it and sent us the results. In Java, there's nothing that touches this. And even in C, we know that in the C we're just a little bit higher at the median, but as things go, the C part, even the ones that we know of, they start increasing dramatically as locks start to dominate some of the time. So we've had really good reports that this stands up in those environments, even when compared to C. We have a lot of things we're working on. Here's just a list. We're sort of looking at it as things that change the core of Aeron and things that are kind of built on top. Persistence. We're persisting a data structure from one place to another. You can build all kinds of archival and replay on that. And that's some of the things that we're looking at. We're looking at what do we need to add to be able to do that. Replication, queuing, stream query. There's lots of different things that can happen on this. That we're looking at. And, we'll see how much of this we get to it. And there's other interests as well. There's people who are looking at building different things onto this. With Aeron, the core of Aeron, we're still hitting on performance. We're still improving things as well. Batch send receive is just a simple thing that you would take for granted. Just setting in a loop and sending as long as you have data. We actually try to send a group of data that's there, we send it, and we go around and do something else. And we're thinking of adding some very simple loops, that you would think, well, why didn't you do that already, right? Grab the data, send it out, grab data, send it out, and then you go back and do something. Well, it's kind of a duty cycle. If you're doing that, you're trading it off for something else. So we've come up with a way where we don't have to trade it off as much. And so doing those in batches, we have kind of some ideas around. How many of you use a disruptor? How many of you know what a disruptor is? Okay. Martin and Mike Barker are the authors of the disruptor. We think that most of the disruptor cases can actually be used and actually be emulated with the log buffer structure, which means that a lot of the IPC mechanisms that you would normally think about, the log buffers could be used for those. So a lot of the disruptor cases could flow into this, or at least the majority of them that are there. We're working on C++ API. We would actually love to be able to do a C++ DB driver. We think that there's lots of different things we could use, like epoll internally and send in message, receive in message on Linux. There are lots of different things that could have dramatic improvement. We're going to be working on InfiniBand so that you can use that, as well as PCIe. As well as we have unicast and multicast, but we don't have any equivalent for like a cloud deployment where you can't use multicast. So you would have to do something like a multiple unicast. We have a very simple way of doing that we like to be able to get to. So those are the things that we're looking at. I can't give you timelines on any of this because I'm going to tell you that the timelines are going to be off. I'm one of the worst at this. And the only person who's worse than that is with this is, well, Martin's actually better than I am, so I guess I can't say he's worse. But anyway, that's the kind of things that we see. So in closing, we took a really ambitious kind of stand. We wanted to do something which was very different than what we'd done before because we thought that it would be work, that it would have a difference to it. And so I tell you that don't be afraid to do that. Think about it like this. Do epic shit. Try those things. And what's the worst that can happen? Okay, it doesn't work out quite like you had, so you may have to work it some way else. But you'll learn a lot by doing it, and things will change. And with that, that's it. So we've got some time for questions.
The latency numbers in the percentile distribution graph, were those inter-process communication on your laptop or something?
Those were going all the way out through the kernel and back. So it was IPC, but not just IPC core. It was also going through the kernel. So it was actually going UDP out and then coming back in.
Through the Mac OS's kernel code from
process. Those numbers are actually Linux.
Oh, those are Linux.
Those are just pure Linux numbers.
Mm-hmm. Okay.
So you mentioned the IETF testing. Are you going to propose this as a standard?
Interesting. The IETF I've been involved with and done different things with. And standards organizations you got to be up for going into a standards battle, right? Battles is too strong a word. You have to be up for actually spending effort to go through that. I'm up for doing that, but we need some more experience to make sure that it's not going to move. So there's So that's the first thing. It has to be mature to a point where you're pretty sure that this protocol has something behind it. Not just the data structures, but the protocol itself, right? Second thing is you have to find a working group that it pertains to. And that's the hard part. There is no one working group that it pertains to. I don't know. So if there were a working group that worked, that it would be perfect for, yes. But it's kind of in the camp that it doesn't have certain semantics that you would think of like web semantics. So it's not like a quick, right? It's not a COAP, right, or a constrained application protocol. It doesn't have a home from a working group perspective. What we've taken the stand of is the protocol is open. We specify it. We have a doc with the specification, and we're not trying to hide it. So it's central to what we do. And so if there were a working group and enough interest in that, sure, I'd be all for it. But I just don't know where it fits. Maybe there's a working group I just don't know about. Yeah.
You mentioned about the million messaging and throughput. Do you have a measure for the latency?
Latency at throughput? You mean?
I've seen the throughput, for example. What
Right.
are the latency?
We have not actually done latency at throughput numbers yet, but we anticipate that they're going to be pretty decent. Latency at throughput is one of those things that most of the time you see this trade-off of you can go to a certain point where the latency is good and then the latency just skyrockets. We know that this latency doesn't do that, but we just haven't run the numbers. And that's just been because of time. We've literally been spending our time trying to find where we can improve it just with either a latency ping pong test where you're looking at the round trips or in the throughput case. But yes, we do want to do a latency at throughput test. We just haven't actually run it.
When doing performance testing on a low latency application, do you typically prefer to write your tests inside the JVM, or do you run something from the outside to kind of generate and capture the performance?
We run them mostly contained.
Okay.
Because one thing is we want to be able to profile it, and if you have multiple processes that you're trying to profile, it's just kind of painful. JMC actually makes that easier because you can actually have multiple processes that can record. But in general, what we try to do is embed it into one process. We actually have an embedded throughput test and an embedded ping pong test that have the driver and the two pieces, the sender and receiver, that are within the same process so that we can look at everything. And we did that specifically to just make our lives easier. So we tend to do it that way, if possible. Yeah.
So, if you recall from the React conference, Leslie Lamport talked about TLA Plus, a specification tool. And there have been a couple of interesting stories recently about people finding bugs in protocols, like Dynamo, for example,
Yeah.
by using that tool. And I wonder if you guys have thought about that problem, or whether you think it's useful here.
I have some experience with doing model checking and doing, that style of analysis. And yes, actually, there is things that we could learn about the protocols that way, but there's even more that we could learn about the data structures that way. Because the data structures themselves could lend themselves to being able to specify that behavior and looking at variants on that behavior and see if they work. Whether we get to that or not, I don't know. But I actually think that it would fit in both those categories. It would be, if anyone's looking for a master's topic, that would be awesome. Because you could do an awful lot with that if you really wanted to.
What would you say is the performance and really the structure in terms of scaling the size of messages? You mentioned 40-byte payloads.
Yeah.
How does that work?
So we deliberately picked 40 bytes for a couple different reasons. The primary one is the smaller messages is a torture test for anything, right? You shifted from being throughput bound to being immediately CPU bound, the smaller you make it, because there's more work that's done per message. So the reason why we picked 40 is because it's small. The other reason we picked 40 is because the header is 24 bytes, and 40 means that now the message fits just within a cache line. So there's certain artifacts that go away, right? Everything is on a cache line. It's all nice and everything should be really nice, and you don't have to worry about certain types of cache artifacts and other things like that. So it lets you, it kind of clears the fog, right? So it also turns out that that's going to be your sweet spot. If you wanted to send and be the fastest, that's kind of where you're going to live, is somewhere in there. And also, most market data messages are small. They may not be 40 bytes small, but they're small. They're not a couple K normally. Some may be different.
So would you say it's say unsuited for significantly larger messages,
Oh, no,
or
no.
perhaps that?
It's totally suited. We can totally saturate a 10 gig by sending even 10, 40 byte messages. We get really close to being saturated, depending on the CPU. You don't have to go much further, and you totally are throughput now. You can't, your as you increase the size of the messages, your CPU starts to drop dramatically because you're actually doing less work because you're throughput now. You can't go any faster. We do fragmentation and reassembling. So you fragment messages as they are sent, and then they can be optionally, reassembled on the receiver side. You're not restricted. We do have a max message length, which is a function of the term size, and that's kind of a number we drew out of thin air. But if you want to, you can increase your term size so that you can have bigger messages. So there's no real restriction. You can send very large messages, and you can do them fairly efficiently. Yeah.
As far as the profile of the device that would be suited to run this protocol, is this something that would scale down to an embedded device potentially?
There actually is a little bit of interest in that, of using it. The short answer is there's nothing that stops it.
Okay.
You could totally run Aeron within any JVM that supports unsafe. Okay. So there shouldn't be any restriction. I have not done it, but I don't see why others can't. Having said that, you may want to think about different idle strategies and things like that, because they would have a big impact on things like battery life.
Yeah.
If you were to try to run the low latency test, which is a busy spin on multiple threads on something like an ARM processor attached to a battery, that battery is going to get sucked dry really, really fast. So that may not be the best use case, but you can do a lot of things to prolong that battery. And because you have a little bit more about what you can control there, I don't know what the battery life would be. But that's what I would be more concerned about, is finding the right way that you're going to do the duty cycles of all the different pieces that are there. But yes, putting it within an embedded device, perfectly fine.
So I hate to be this guy, but when is the use case switch from AMQP, like a Kafka, to Aeron, like a possible use case?
So something like Kafka. Kafka is sort of a clustered solution, brokered solution that's persistent. Multiple hops potentially. It kind of scales with. It doesn't scale linearly, but it kind of scales to a certain point. I don't know enough about where it would start to not scale as well. So Kafka has certain advantages, and it has a really nice architecture. From a brokered clustered model, it's a very nice piece. It does have some contention within it just because of the way it's designed. The persistence aspects of Aeron, since I said it's a persistent in the terms of a functional language persistence in data structure. What we're looking at persistence in terms of striping is based on terms. So that should stream much better and have lower contention than something like Kafka does with a clustered solution, which means that as Kafka, as you add things to it, at some point it's going to kind of tail off, right? Amdahl's law and universal scalability law at some point will kick in, right? We've intentionally designed Aeron so that we don't think that will happen. Now, whether we've done that or not, and whether that actually is true, we have to bear out. But we think that there shouldn't be anything that stops us persisting, and I mean in a volatile storage way, like a Kafka from Aeron being used in those use cases. It should still scale. We just don't know what yet. And it will take us until we actually get to that. But so that's that. AMQP being a different topic. AMQP being a normal topic-based pub subsystem. The only difference being that parsing an AMQP message is not a simple thing. It's a very stateful parsing. It has some other things within it. It can be done fast, but it can't be done like these data structures. So it has a variable length header. I mean, it has a variable length message that would be kind of hard to put into this data structure for some of the things that we do.
Perhaps this is a better question for Martin, but do we have any idea if the JVM developers are ever going to put the pause instruction in unsafe?
That's Gil first.
I think the GIL actually is pretty open to doing something like that. But to get it into something like unsafe for OpenJDK, I think that would be a much better question for GIL. I think pause would be a really good one, because what pause does is it defeats speculative execution. It makes some of the busy spins better, from many different angles. It's also friendlier and greener, to the CPU. But actually, personally, there's a lot of things I'd like to do with the SIMD instructions. So I'd actually like to see a whole bunch of intrinsics added to OpenJDK. Pause just being one of them. I think it would be great. First thing I did as kind of working on the C++ client API was to actually go, yes, I can do pause, and put it into the duty cycle and then the idle strategy, since I had access to it. So yeah, I don't know. It's been very disappointing to see sort of the reaction. If you were on Twitter a couple days ago, Martin had brought up the fact that there's still these things that are there. And the reaction from the OpenJDK community was, well, file a bug. Okay, well, I filed a bug. Oh, that was rejected. Why? Around string encoding and things like that. So, I mean, there's, it's, I don't know, it feels a little weird, with the JDK community. I don't spend enough time there, so I don't know. But love to see, additionally things come in. But I think the progression is towards getting rid of unsafe, or at least deprecating it, or pointing people to not use it, which, that's kind of defeating a lot of what some people want to do. They really want to take advantage of it, because they like the rest of what, the JDK gives them, and what the JVM gives them. So it's complicated. It's weird. Any other questions?
Can you speak a little bit about kind of the state of the C++ port, and there's differences in numbers?
Yeah, I have to apologize. I haven't gotten to it as much as I wanted to. The state of it is that with the help of a few people, the memory ordering instructions are the same as what you get from JDK. So the memory access ordering, everything else is equivalent. Some of the base data structures are there. We have also some of the being able to send the commands to the media driver and be able to get them back. The next step is to be able to do sending. So that actually isn't that hard. It's just simply getting time to do it. And unfortunately, I just haven't had the time to get to it as much as I would like. So the state is that I really, really want to work on it. The reality is I just don't get to work on it as much as I would like. But the goal is that we get the C++ port. Our goal is actually by the end of May that the C++ port is usable, so that people can start playing with the C++. That's actually been our goal for a little while. It actually was the end of March. That's not going to happen, so got pushed back a little bit. But we're thinking at least by the end of May, and trying to set that as a firm deadline.
On that same token, do you know of any interest to build a Go client, at least on the consumer side?
I would love to have a Go client. In fact, one of the reasons why I want to have C++ working is so that there is a way to integrate in with Go and Erlang. I actually have a fondness for Erlang, and so I really love being able to do that. And I see the C++ client as being the first step. There actually is work. I don't know the details, but I have heard that there is Google has been looking at adding a memory model to Go, which means that at some point there may be possible to have a direct native Go client that talks to a media drive. And if that works and it's fast, I would be all over it. I think that'd be great. So I kind of like Go in a lot of different ways. And I'd really like an excuse just to play with it more. No C sharp? No one wants to know about C sharp?
It's open source.
Apple,
Oh yeah, the raffle, yeah.
if you want a free registration for Go to Chicago, see more great presentations. All right, well, I'm gonna have you pick a number from 1 until 26.
Okay, give me a minute.
All right.
1 to 26.
1 to 26.
Let's go with 16 since it's power 2.
All right. 16 is Dominic. Great. So I have your information and I can email you your free registration. And can we go back to the first slide? So also just to let everyone know, just by being here, you guys get $100 off registration for Go to Chicago using the code ILOVEGOTO. So if you want to go to our page and register, you will get $100 off registration. I also wanted to point out that Dean Wempler is here. He is another speaker. He's right in the back row. He's another speaker at Go to Chicago, and we really appreciate him coming out tonight and being here. Thank you, Todd, for coming all the way from San Francisco. And thank you guys for coming out tonight. And also thank you to Trading Technologies for co-hosting this event with us. Yeah.
Thank you. Thank you.